we're going to start the session on the TART electronics now. I have the great pleasure to introduce Dr. Stanley Kuja here. He's going to be presenting an overview on the TART electronics and all the development went into the first, and then also be running a little electronics demonstrator with, for you guys. So yeah, thanks so much, Stanley. Take it away.
Thanks once again, Ben, and the team for organizing the workshop. So I'm a staff here at Transient University and also part of the RAT team. Thank you. So this particular presentation will focus on the Transient Array Radio Telescope, which is known as TART. And we're going to basically focus on three things. One is, what is TART? Two, why are we interested in TART? Why do we have it at Transient University? And lastly, how do you use it? How do you calibrate TART? How do you use the TART data? I think the last part will be handled by Ben and team. So I'll only focus on the first two. Why are we interested in TART and what is it? So I'm going to give an overview of the electronics involved and the connections. Prof. Justin has already given, actually covered a good chunk of my presentation, which I think means how relevant these concepts are in this particular workshop. So why are we interested in observing within the radio spectrum? Yes, I think so these are just basics to lead us somewhere. One is that within the radio spectrum, it gives us detailed information as compared to the optical spectrum. So earlier in the days, we used to do astronomy using the optical spectrum, but in the modern radio astronomy, we've shifted that to actually use the all of electromagnetic spectrum, where the radio waves fall within the electromagnetic spectrum. So we know in the electromagnetic spectrum, we have the gamma rays, X-rays, visible light, infrared, microwave, and the radio waves. So if you look at this particular example, the first one is an optical image. You compare that with the radio image, you see automatically that there is detailed information in the radio image. I look at it, I see the intensity, different intensities of the colors. Perhaps it gives me the intensities of the dust, particles, or gases around that region. The other thing, I'm not in science or astronomy, but I can pick a few things that these galaxies are actually interacting. So there's probably interchange of energy. I'm not sure, but that's the things I can pick from this, even without being a radio astronomer. Whereas in the optical image, they're not stars, these are galaxies. But I just see that it doesn't give me more information as in the radio spectrum. So that's the first reason why radio astronomers are interested in the radio, doing observation within the radio spectrum. The other important thing to note is that we are able to do ground-based observations. If we take, for example, if you are in the beach and you need to see, and far off distance, you see some moving objects, you are not sure whether they're animals or people or whatever, but when you start moving closer, that is, you're using the optics of your eyes, you start to identify certain characteristics. Then you say, perhaps they're not animals, they're actually people. As you move closer, you identify it's a male and female. As you move further closer, you see that, okay, one is putting on a black or shirt or whatever. As you move closer, you identify even the color of their eyes. Now, what that tells me is that the closer you move, the better you resolve the image. But now there is a limitation when you use the optical spectrum, because we can only, it's limited within our solar system, and astronomers cannot go deep into space to get closer to these objects and identify the images. So we then use the radio astronomy, use the radio waves, because within the electromagnetic spectrum, you realize that in the atmosphere, most of the radiation will be absorbed. But within this spectrum, where we actually have TART and other interesting science going on there, the characteristics of electromagnetic of radio waves is that they can penetrate through the medium. So they can be attenuated because they travel, there's longer path lengths, but in as much as they reach the earth as weaker signals, we can use powerful instruments like meerkat to detect them. And the fact that you can also do ground-based observations, it's now affordable and convenient for scientists. Now, the third reason why we're interested in doing these observations in the radio spectrum is that there is very high resolution through a technology known as interferometry. So interferometry then gives us this important parameter known as resolution. All right, so let's talk about resolution. So what is resolution? We're going to tackle it in two ways. One, as a single antenna or a single dish, and then as interferometer. Now, by definition, you can get the resolution of a single dish antenna in the order of this term here. This is a wavelength divided by the dish diameter. This wavelength is the wavelength of your observation, right? Now, if we take an example, if you want to get a resolution of one single dish antenna, where you want to observe at this wavelength 1 micrometer, that will be within this spectrum here, right? Now, if you do that with a dish which is just 2.4 meters, that gives you a resolution roughly approximately 0.1 arc seconds, right? Now, if you are to have the same resolution at a longer wavelength, because remember, radio waves have longer wavelengths, and that already is a problem for us as a scientist, then you will require 2-kilometer diameter dish. I mean, that is probably impossible in terms of the mechanics and the construction and all that. If you are to even build a slightly larger dish steerable antenna, you see, obviously, building one dish antenna that you want to steer or to do this observation becomes problematic because of the long wavelengths. You see, when we design antennas and characterize, the first thing you want to deal with is the size of the antenna, which is related to the frequency that you want to observe. And it is always the resolution then becomes a factor of the inverse of frequency. In fact, if you are to design meerkat antenna using this computational stuff, I have to scale it down. And when you scale it down, frequency goes up because it is an inverse. And so what that means that the longer you go, like increasing the wavelengths, you need a single dish antenna. But this has been resolved in radio astronomy by using this technology known as interferometry, where now you have, I mean, Justin already touched on it, you have different small dishes, you bring them together, right? Then you correlate the data. This gives you high angular resolution. So it gives you the same frequency as you would have had with the large antenna structure. So how is this used? So you have an array of antennas, and then you focus at the same object, and then the the signals will arrive at individual antennas differently because of different path lengths, and then that time delay will give you the positional information of the objects that you are interested in. Now, I said for the single dish antenna, the resolution is lambda divided by the dimension, the largest dimension of the reflector or the dish. But for the array, we look at the baseline. Baseline is the distance between two antennas. So you look at you divide the same lambda by the longest baseline. Now, you can also look at the maximum angular scale, which is a lambda divided by the minimum baseline. Now, this range then gives you the angular scale, right? The range gives the angular scale that your interferometer is sensitive to, right? But if you want the best angular resolution, you go to the smaller values. So in the context of interferometry, the things that you have to consider is the sensitivity, which again, Jonas talked about, and that is simply the number of antennas times the area covered by the antennas, and then the field of view, which is simply the resolution of one single dish antenna. Then the resolution is very important in interferometry, and you look at the range of angular scale that your interferometer is sensitive to. Those are four important things to look when you want to design an interferometer. What I've said in summary is that radio waves are electromagnetic waves. But in as much as modern astronomers do radio astronomy using the all spectrum or electromagnetic waves, because they use infrared, they use microwaves, but radio waves are very, very important because natural phenomena, including natural things, emit radio waves. And optical spectrum is limited within our solar system, but when you want to study the universe, the unknown universe, then we have to tap into radio waves because they're only waves that can travel way far off from the unknown universe to our system, right? Others will be absorbed within the Earth's atmosphere. I think that is clear. An example of the angular scale, like when you have a good resolution, then you get a better image. This is the first one is an image from the large millimeter array. Each dish is 12 meters and has smaller spatial scales. And then the second one is a compact array. Each dish is 7 meters and has larger spatial scales. Now, if you want to get both, you need a combined image like this, right? So that's how angular resolution is important in interferometry and in radio astronomy. Now, let's go to TART. The reason why I was introducing that is because TART is an interferometer, right? And we tap in the radio waves and analyze them. So before we talk about TART, let's have an idea why TART is of great interest to us and why it complements MeerKAT. Now, the first thing is that top scientists, like our own Prof. Oleg here and the rest, and different initiatives compete for the MeerKAT data. So that has to be clear. So as you as students and for teaching and training purposes, then it's a very important tool because they write proposals to use MeerKAT data. You as probably a master's students or whatever, writing, even if they grant you, they'll give you a window. Maybe you're just going to use MeerKAT data within 3 months. And so initiatives like the Breakthrough Listen that was initiated by Stephen Hawking and Yuri Milner, they have more access. They'll have more access to the TART data than you as students. So we realize that if you need to get access to data that is available freely anytime, then TART gives us that opportunity to do so. And two, it's a hands-on experience. It gives hands-on experience to students. Like you can build the TART once you have the electronics, do the connections, and you don't need to worry about breaking some of the parts here and there. Why? Because it is also low cost. So if something is broken, you can quickly order and fix it. And having access to the electronics anytime for student training, for research, because here at ROSE we just have it somewhere up here. Whereas for Meerkat, even to do simple RFI measurements, it's not easy because you have to apply so that they give you a time frame when you can go to on-site and do particular experiments. And also there are certain restrictions, that come along with it. And the distance from here, say from Grahamstown, you want to go there as a team, it's very far, so it needs proper planning, and that makes it very expensive. Two, the project itself is very expensive, whereas for TART it's cheaper, it's affordable, and the interesting thing is that we do all these things at very low power. Remember, Jonah said the electronics that go to the Meerkat is power intensive. This one, you just need some 24 volts power supply, and it will run. The fourth one is a very important aspect, that there has been lack of collaborative programs to deploy training facilities across African partner countries like Kenya, Mozambique, Madagascar, Mauritius, Zambia, Namibia, Botswana, and Ghana. So because it's low cost, then we need to build a capacity in these African partner countries by having TART. They are deployed at various universities within the APC. So we think that as RAT Group, in collaboration with Sereo, this is a possibility that we can do these projects, and it will be beneficial to our partner countries. South Africa is busy doing all this stuff, but it's like they're lagging behind because of lack of probably maybe say political goodwill, and especially to our institutions, and also funding, finances, and all the politics that come around with it. So it's easier if we really want to move forward as Africa in radio astronomy, then we need to get more involved, and we just need to invite Sarao and SK and other interesting parties how we can roll out this program. Remember, just building an array of 2 telescope dishes is very expensive. But this one is an array of 24 antennas, so it's ridiculously cheaper. So that's why we are interested in TART. I think I've given a good background on that. So let's have a TART system overview, hardware. Now, this is the TART that we have. It's up here, working distance, I think. It's a good exercise. Maybe in the evening you can go and see it. This is the TART. We have the structure that is holding up the antennas. These are 3 beams. All right. In each beam, we have 8 antennas. These are GPS antennas. And in this box, we have the electronics. The box is dust and watertight, but it serves 2 purposes. One is that it gives the mechanical support, but 2, also for EMI and other shielding of interferences, both from the electronics that is housing, but also radiation from outside, because it is a metallic enclosure. Now, there are a number of projects here. One is that we have more of a Y-shaped configuration here. So these beams, you can move them along to change the shape. 2, you can also move the antennas shift the antennas along the beams. We've not experimented with different configurations to get the better resolution of the interferometer. So this is a student project. If you change it to a T shape or another shape, or you see what do you get from this versatile equipment. 2, we have 3, but we have the provision to have 5 beams. You see, that's another possible student project. So if you add 2 additional beams and then have different configurations. So just playing along with the configuration, it's a good student project. The other thing is that these antennas are what we know as the AIA, active integrated antennas. So just because an antenna is just a structure. You see, if you've ever listened to analog radio, you just take a wire. If the other one is broken, wire, attach it to the position where the antenna ought to be, then you pick up your radio frequencies. So that structure alone, like a meerkat dish, this structure alone, that's an antenna, but is a passive antenna if it does not have what is known as the amplifier. So an active integrated antenna is the antenna plus the amplification part. So it becomes active integrated antenna to amplify the already weak signals. This is a student project because we ordered these particular antennas and use it as it is. Whereas if you had designed this in like FECO that Prof. Jonas gave credit to, I think one of my students here used FECO. So you can design your own antenna, right? Characterize it, and then go ahead and give a prototype and final. With the good thing with that is that you can change the parameters the way you want. If you find that it's not giving the better, it does not have better radiation pattern or the gain and etc. These ones we can't change. You use them as they are. So that is also a student project. Now the third part is that we were really excited and we went ahead with the installation, and we didn't. For the first thing, as Jonas said, when you want to get a radio astronomy site, you must characterize it to ensure that it is radio quiet. So when we were picking the site, we said, okay, down this side, there's more of the potential RFIs because of all this stuff. So let's go up there where it's just 2 or 3 people living, but we didn't characterize the site. So we need to characterize the site. We also need to characterize this box. We just bought it. It's not characterized. We just believe that because there is a metallic enclosure, it will do the job. So we need to characterize this. We need to characterize the site. That is also a student project. Then we also need to do conducted emissions, like within the antenna structure and the cabling here. I will show you how we can do that. How is it properly connected, or do we have radiated emissions into that get converted to other what is known as common mode currents, unwanted common mode currents, and that can happen in 2 ways. 1, because of the coupling of the cables. 2, because of the radiation elsewhere that couple into the cables. So that is also another student project. So on the electronics, we have 3 important parts. The first one is the base station, which I'm going to show you, the radio hub module, and the radio module. And then what we also managed to do is to work on the infrastructure so that we can sustain it. I mean, with the load shedding in South Africa, we were worried, if it's switched off, you need to recalibrate this every other time, and calibration takes more than 6 hours. So you can imagine every load shedding, we have to recalibrate. But within that, we had some CPUs, UPS sitting somewhere, and we connected it, and there's a generator there. So every time we have load shedding, it is up and running. It's not affected. And then also we figured out how to have the internet just to transfer the data. So whether you're in Europe, you can access the TART data. Now the interface. This is the overall interface. So just if you're listening to Justin covered on the larger scale of things as we're doing it in a smaller scale, but it has every other thing that Justin talked about. You can imagine. So we have 24 antennas. These 24 antennas are connected to radio module, which are simply the receivers. And then we have the radio hub. So we have 4 radio hub modules. Each radio hub has 6 antennas. You multiply that, you have 24 antennas. And from here, what we are going to get out, so we have the power that, we power the radio hub module, which is shared within the receivers. And then we need to have what comes out to the base station is a digitized signal, because now we need to have the FPGAs to do the calculations. And then because there's computers only understand the digital language. So we need to convert that analog signal. The signals we get from outside is analog signal. So we change that into a digital signal. And then we are happy because now you can sit in your computer and do your analysis. All right. So that is connected to the base station, which has 2 important components. The FPGA, which Jonas again talked about. FPGA is simply an arrangement of logic blocks. So it's a programmed device. That is different from when you talk about the microcontrollers. And the advantage of it is that if you have, for instance, in the old days, you have a microcontroller, and then so you have a device, then you write the function to operate the device. So if you in signal processing, so if you have 2 inputs, let's say X and Y, and you need the output as Z, then you write that function that works together with the microcontroller. But remember that there is a processor in the microcontroller. Now, if you have 2 functions, this becomes a bit hectic for the microcontrollers because the CPU has to read all the functions, and that might be complex to handle. Now, with the FPGA, you can run parallel calculations independently. So you can program your diode here, light diode. You can program this side to run a different function. So it does all this independently, but also in parallel, which means it is also very, faster. And then it's already a programmed device to specific function. And then you have the Raspberry Pi, which is just, by now we are familiar with the Raspberry Pi. It's just a computer, it's a single computer. It has all the features that you want to, that you will want to run. So with the just almost this size, small size, it has the processor inside. It has the USB connectors. It has the Wi-Fi and Bluetooth module inside. It has the memory card, which is like the hard drive. That memory card, small memory card, it has the operating system for the computer. So if you just take it the way it is, the way it is, and connect your desktop and you connect your mouse and the keyboard, you just run it as a normal computer. So why do we need it? It provides with the FPGA so that you can now transfer the data. So you see how small and compact it is. It has everything that Meerkat, has, and it's a very affordable, at a very affordable cost. So now the actual electronics, that was just a diagram. So here we have the actual radio hub module, which has 6 radio modules, and each receiver is connected to a particular antenna, and then we name those antennas. In fact, even Meerkat, when you talk of array, you must name your antennas. It's just good for analysis. So in fact, the first Meerkat dish was M63. And there were supposed to be 64 dishes, which means the numbering starts from 0. So 0, you count 64. So even here also we number them. So you have the first antenna 0, 1, 2, right? So if there is a particular antenna with a problem, you can identify it's antenna 1, antenna 2, antenna 3, antenna 4. We do that in the radio module, and then it has 2 ports, the clock and power, because you must power it and you must get out all the digitized signal. This technology is a very beautiful technology, because it is the only technology that allows us to analyze radio waves in a better way. And this technology of the receiver, the part of the receiver system, is known as heterodyne technology. So what it does is this. I said this is a active antenna. So you amplify your analog signal, then it comes in. Now, in the older days, what they used to do, once you have the signal here, then you put a filter, because you only need a particular frequency, right? So you put a filter here with a narrow band. But the problem with that is, if you need another signal, you have to tune your filter. Now that already affects the stability of the filter, right? Two, the filter also, manufacturing narrowband filters was a problem. Now, what we've done here, the radio waves operate within the intermediate frequencies. So you lower the frequency, so you have this higher frequency, and then you have a local oscillator, and then the principle is based on a very simple mathematics, which is this. So if you mix those two signals, it brings down the frequency of the signal, but it does not affect the amplitude and phase of the original signal. So the information is still there. And so if you, the cosine identity. So if you have two signals, let's say cos X here as the input signal, cos Y from the oscillator, then you get these two terms, right? Cos X plus Y, but we are interested in this term. Now, this one is what is known as the down conversion of the signal. So as an example, so in the L band, we have 1575 megahertz. So remember, the antenna connects all jargon, right? Everything that is available, any radio that is available, depending on the operational bandwidth of the antenna, but you are only interested in this particular band. So you have 1570 coming in, but you have to lower it, right? So you bring the local oscillator. Now, what it will do, what the mixer will do, it will down convert the signal. Once it's down converted, then you filter out. Now, the beauty with this is that even for the manufacturer, you only manufacture one filter at specific bandwidth and center frequency. So all the signals, so if you need a different signal here, it is, you just tune the oscillator, right? So it's easier to tune the oscillator, right? But what comes out, you just use a single filter. And then after that, you then change the analog signal to digital signal, and then this goes to the base station. Now, that is heterodyne technology, very powerful, that it has made wonders in radio astronomy. All right, so this is what we have here. So each module has a receiver, and that receiver, the signal gets down converted so that we can better analyze the signal, right? And then we take this into the base station, where we have the base station, where we have the FPGA, which I've said what it does, and we have the Raspberry Pi. All this. So this is on. If I say this is the front side, you just flip it. So the other side is this side. It's the same thing, just much of, flip it. So you have, you power it here. This is the section of FPGA, just like you can power your computer, and this is what is distributed in the other parts of the electronics. And we said we have 4 radio modules, and each radio module, you have the clock port and the power to power the radio modules, right? I hope you can figure that out. Now, that's part of the electronics. And here, so you have the chip, which has a memory, which has the operating system for the whole thing. And then this guy here communicates with this guy, so you can transfer the data. Now, how that happens, I think Tim will handle that, accessing the data and how you use the data. This one, we have, the RAT has a website where you can access this. We're still building it. It doesn't have all the information, but also how you can use the interface now to download the data and manipulate the data. Now, TART, you can do a lot of things with it because you can track down transient events. You will then be able to even identify hidden satellites, which means for security purposes, even around the ground star, can say, oh, that's what's that? Because we are supposed to know the satellite. So if there's a guy who has just thrown a satellite up there and is hidden somewhere, TART will pick it up. They developed algorithms from this because students can access data anytime, write code and everything. I think Tlaba worked on RFI, finding RFI using machine learning and use state data. So that algorithm can be applied in Meerkat, but also in other fields like banks, self-driving cars. The beauty is that it's done at low power. Remember, when you build an array like this, it becomes computationally expensive. So that's another good advantage with TART. And then the way we see things, because of the astronomy is pushing technology to its limits, then we realize that in the next industrial revolution, it will play a very critical role. So you are in the right place, in the right place. And I think last Sarao conference, you are told how many, many of our graduates in radio astronomy have been employed in banks and whatever because of the things that you can do with the kind of stuff that we work on. We are in the process of developing TART-3. The electronics, the design and the prototyping, manufacturing is done by team and is a research group from the University of Otago. So in fact, we built and deployed this facility because of that collaboration and Stellenbosch University. And as I said, we're still discussing how that can be deployed in other parts of Africa. So we see how RAT is gaining momentum, not just within South Africa, but if this happens, then we are spreading our arms to other parts of Africa. And then because so in the planning process, if you can organize more workshops that students actually have hands-on experience building this, breaking that, and then in the process they learn how to build a telescope, and also when they're exposed to huge telescopes, it's not intimidating to them. All right, so now that we've had enough of that, we need to do a little bit of demonstration. So we ideally we ought to have had here the electronics because it's a workshop, and then we partition you in different groups, and then you build your telescope and all that is all right. And that will probably take a whole week because every process you need to understand, right? But now we already have our telescopes installed up there. But what we're going to do is to have a little demonstration how an antenna receiver thing works using a single antenna, right? Just to have a rough idea how things work, but also to demonstrate some of the equipment that we have within RAT that we use to do some EMC or EMI testing. These are very, very powerful. This is not the ordinary equipment used in the lab. These are for precision measurements for EMC and RFI stuff. So for simple demonstration, what we have here is a real-time spectrum analyzer. So it's not a normal analyzer. And that spectrum analyzer, we use a phase stable cable, because if you have a cable that is not phase stable, every time there's movement, it will. That's why we say precision measurement. Any movement of the cable will affect your measurement. So you use a phase stable cable, and then we have a stand. So this is just actually this setup. So this is the phase stable cable connected to a USB real-time spectrum analyzer that is powered. But also because it's meant for field measurements, there's a battery here, and it can last, I think, for 8 hours. So you can actually do measurements without actually, even during load shedding, you should be able to do measurements. Now that is connected to, this is a biconical antenna, which is large band, and biconical omnidirectional. It's an omnidirectional antenna. It can pick radiation from different direction, so that we connect with the spectrum analyzer. The spectrum analyzer, as I said, is like a receiver. So it works also based on the heterodyne technology. You do the down conversion of signal, and then it's easier for you to analyze. But we also have the aspect of up conversion of signal, because you might ask, where is the other term? It's used somewhere, but because we are filtering out, we will not see it in the what we observe. And then this, because the data captured here is a lot of data, we need to transmit it at a very fast rate. This cable, you must connect it to the other port is 3, which is the super speed port. You don't connect it to the second one. All right. So for the laptop just enables us to see what it does, just more of like the displaying the results for us. So what we need, so I have a spectrum analyzer that operates up to 7.5 gigahertz. I have a wideband biconical antenna that operates from 20 megahertz to 3 gigahertz. And then hyperlog antenna, I'll explain why you probably need that operates 40 megahertz to 6 gigahertz, and then cables and connectors. We have different types of connectors in electronics that you need to have for proper connection. And then if you have time, you might do conducted radiations using the current probe that I think operates up to 1 gigahertz. So I'm going to do 2 demonstrations using this. One, we're going to do demonstration on the which band? Bluetooth LAN is a problematic. So we're going to do Bluetooth and LAN because they also share, by the way, bandwidth, and that already is a huge problem. And then we're going to do demonstration on the FM so that you see what we're talking about. Now, this is the normal spectrum. We see normal spectrum analyzer, this window here. And so if we are not familiar with the spectrum analyzer, there are 4 things you need to look at. One is, by the way, when you're doing measurements, you must know what you want to find. just don't go and so first you must know what is the correct connection. Even this setup is probably not the best setup. I'll tell you from the EMC point of view, and then you must know what you are looking for so that you just set the parameters right. So the first one is the frequency. Now we want to do sweep across the Bluetooth. Bluetooth is and Wi-Fi is 2.4 gigahertz to just about 2.4835. That's a very narrow band, and there is where we fix the Bluetooth and LAN. And then from there you can get, if you get 14, assuming we have 14 channels, each spaced at 5 megahertz, then we can say probably put our first the center frequency at 2412, spaced at 5 megahertz. The second channel will be 2417. The third channel will be 2422. Are we together? So then you must tell the spectrum analyzer the center frequency of interest. Then you can span around that center frequency to see what you capture. Remember I said you will have, you have to identify the frequency that you want to operate. Then we have the reference level is just a, so along the signal path, you must provide some gain or attenuation. Why is that important? So that you can capture stronger signals without going on the overdrive. But you can also capture weaker signals, right? With the better signal to noise ratio. So you must play along with the reference. If you've done this for quite some times, you will know what to put in. I'll put there minus 40 dBm. This frequency, we said, what did you say?
I think you did put the gigahertz jump.
Oh, okay. Say 2412 megahertz. Okay. Now span. So you've chosen your center frequency, but how do you want span? So it's the spectrum around the center frequency that the spectrum can see. So that's also important. You see. So we can put the span. We leave it at 40 megahertz span, and then resolution bandwidth is now the minimum frequency separation that the spectrum analyzer can detect. So it's just the same principle with the resolution on the other side. So the smaller it is, the better for you, because you can capture every other frequency that you might have left out. The bigger it is, then it becomes a problem. You leave a lot of spectrum that you will not capture. So then this is what we see. Now with the normal, so then we need to, so this is a normal, so the other thing you might do, I said that antenna is just a structure. So that structure, this is not active integrated antenna. So we need to amplify the signal, but you can see through the cable, I've not amplified it anywhere. The beauty of this is that there is an internal amplifier. So let's also amplify the signal. So we'll go to amplitude and then put it on. So you start seeing there's something here, because now the signal is weaker, but it's speaking something. Now, when I amplify it, now you start, it's appearing somewhere there. And you can also see there's something here, but it doesn't give me much information. So for me to get a little bit more information, I go to another technology, which is designed with this, so that it can give me a better information of the things that I'm seeing here. So I'll go to, and that technology is known as the DPX. So I add that. Now the DPX gives me more information of the spectrum, the activity that is going on here. So I know some of your Wi-Fi is on and LAN. Now it gives you more information than this. You agree? Yes. And you can see the Bluetooth and all that. Now, interestingly, if I were to scan the environment, this guy here will not capture fast transients, right? This guy will do that for me because it can capture as smaller as 100 microseconds. So what I'm going to do with that, if I put on the Bluetooth, just look at here, and these at the same time. I don't know how you need your eyes, but okay, let me change something. Let me say, because the way it is, it can capture, but you don't see it. So let's say that it capture, and then whatever we capture remains unity. So we'll go to settings. Oh, there's more analysis you can do. So let me also add that. This is called oxogram. So I'll add bitmap. Let me make it more, increase the dynamic range 3%, and amplitude scale, also increase the dynamic range to say minus 40 dBm, and then we do two traces. This trace, a bitmap trace, and then infinity. So we see if it will capture. So whatever is captured here remains. So if I take my phone, put the Bluetooth on, and that Bluetooth on, I try to send some. So let me take a picture. Try to send to something which is not there, because it will still send the signal, just that it won't be received the other side. And then share using Bluetooth. Then you see they are picked and they remain here, right? That is the data that is transmitted from my phone. Then what this tells you, so this is the frequency, this is time. You could, so there's a signal here that has just gone. I don't know where it's come from, but if you see something of interest, you can stop. You can stop, and if you stop, so this will give you a rough idea of the signal that you saw. If it is recurring, you will see it again, and because this is a function of time, then you can measure the time difference that it occurred. So if it's occurring within 1 minute, you will know. But if it's occurring within 10 hours, you can't sit there and wait for the signal to occur. So what will happen, you can set the oscilloscope, like you mask it. So you mask the non-signal, and then you tell the spectrum that when you see something that is beyond here, capture it and then stop running. Or you can tell it when you capture it, make a sound and then you stop running. So later on, after you've taken your coffee, maybe 6 hours, you come and see, oh, I captured it. Then you start analyzing that particular signal. Now that's how you start to analyze the electromagnetic environment of a particular place, but also to do EMC measurements. Now, if you increase the resolution, are we still within time? Yeah. If we increase the resolution bandwidth, so let's say we increase this to, no, we reduce this to 10 megahertz. What happens? Then you start to see more spectrum because now you can go into detail, right? If you increase it, the resolution bandwidth, then you will miss out some of the spectrum captured here. This is a very powerful tool because imagine you can scan over 40 megahertz. That is ridiculous. You know, so all the transients, if you want to analyze RFI, we have the tools here at TART, and these are very expensive tools, by the way. Now, student projects. That antenna is a commercially available antenna. So if just to give you a rough idea, so I want to do quick scan of the RFI environment here within a particular frequency band, then I use the omnidirectional antenna to capture everything, right? Once it has captured everything, now I'm going to identify specific frequencies that I want to focus on. So with that, I transition from that to because I want to locate the exact position where that radiation is coming from. I can't do that with a wideband omnidirectional antenna. So then you shift that to, you go to a unidirectional antenna, and this is a long periodic antenna. So let's say I've done my scan with that, I've identified specific frequencies. Then you, of course, you attach this one here, and then if the signal is strong in this particular direction, you see the amplitude increase. If you shift a little bit, because this is unidirectional, the amplitude will reduce. So you know it is not in this direction. So you keep on going in this direction, and then that's what you call direction finding of RFI. So you move with this until where you'll see where it's strongest. And these are for field measurements. Now, this guy here and that guy, we have bought them, and they're very expensive, by the way. So we need students to characterize them. We don't have facility for characterization, which is an echoic chamber, but we can borrow through collaboration, the tech facility, Stellenbosch University. Then we need students to go and characterize antennas and tell us that the data provided by the manufacturer is actually true. That's a student project. We also need students to design, characterize, and manufacture, so that we have our own antennas that we have designed and manufacture. That is another student project. And the beauty is that we have the softwares, and when we don't have the facility like characterization, through collaboration, we send you, do the one stuff there, and come back. But we are building the facilities gradually. Now, let's look at another frequency of interest that we are familiar with, is the FM. FM operates within, that's a megahertz frequency. I mean, you drive cars, you know that. And it's within 87 megahertz to about 108 megahertz. So you look at that span, you realize that the span will be, if you do the calculation, about 20.5 megahertz. And we pick the frequency here. So the middle frequency, so 87 megahertz minus if the span is that, you divide the span by 2. Remember, when you look at the bandwidth is with respect to the center frequency, so there's the positive side, the negative side. So that will be 10.25. You add that, you will get something like 97.75. 97.75. 97.75 megahertz, and you see what we picked already, right? So we've picked here a bunch of frequencies. These amplitudes are actually, I assume those are particular frequencies for radio stations, but let's see, maybe it's not. So if we go to, and from here you can pick up the highest frequency. So just put a marker, right click, and say marker to pick. What is my highest frequency? My highest frequency is this, and it is about 107 megahertz. I suspect this is a station, all right? But is it really? Let's find out. So if we go to audio and FM demodulation, because we have to demodulate the signal. Remember, this guy takes the analog, he's a modulated signal, it goes through that, then through the receiver, you have to demodulate the signal for you to get the frequency from the carrier wave, all right? So what has happened, I've chosen my center frequency, but I need to align it with the frequency of the spectrum line, and I didn't do that. So let's try it again, but also the interference from myself. So 97.75, then align that with center frequency and then run. Yeah, but so the radio stations, just there's a lot of interference, and that already tells you where we are, all the activities that go on, plus the connections. It's a problem. Now, what I want to do, look at these two signals and the impact of the resolution bandwidth. If we go to lower, let me average so that it's more visible. So we go to settings, trace, average. So it's more visible. These two. If we increase the resolution, if we reduce the resolution bandwidth, they ought to be more visible. Like say 10. So you see these two, and you can put a marker here that is at 89.7 megahertz. Then you can add another marker to see what's the separation of the two. Add marker. Or even the second one, this one here. That is 250 kilohertz. So the difference between this signal and this one here is 250 kilohertz, which means if I increase the resolution bandwidth to 3 megahertz, I should be able to make this signal and this be one. Like I won't see it, right? So let's increase the resolution bandwidth to 300 megahertz. So you see, there were two signals here, but forget about this. It was this and this. Now it is one. Now, if I also increase the resolution bandwidth for this, it's going to be one signal. So the spectrum analyzer is not sensitive anymore. So that's how important, when you talk about resolution, how do you resolve the the signal in this particular case? Now, in the interferometry, you see how do you resolve the image. Lastly, now that this experiment has failed, but you hear some voice. It's actually it's actually a station. So that is for the radiated emissions, this antenna and all that. But we can also do if we remove the antenna, actually, it's going to get worse because we can't capture anything. So with the conducted emissions, you want to measure common mode currents, things like that, and to make sure that the cabling and connection is done properly. Then you're going to use also and then when you talk conducted emissions, you must also know the frequency range. It's always in the kilohertz to a few megahertz because now it is current. So you change. So let me go to presets. The frequency, kilohertz. Let's say 10 kilohertz. And no, not really. Let's go to start frequency. 10 kilohertz to a few megahertz. Let's say like 100 megahertz. And then we put we put the internal amping, and then the reference level, let's say minus 30 dB. If you want, you can add the dpx. Did he add it? And so we can scan this maybe a bit, let's say 40, or even lower than that. Can reduce this to probably 100. We're not seeing anything, right? But now this is known as a current probe. So it can pick up all the common mode currents that maybe is in your cable. So just open it. We did a lot of measurements using this. It's also very powerful. It's very small, but it's the value is just above 70,000 rand. There's just this small thing, and what you can do if you want to study this cable here, just wrap around it. Then you start seeing some spikes. But if it is this is a signal cable, so you expect that it is probably better managed cable. I can go all through and identify which laptop, the poor cable, not well connected, or is picking up a lot of radiation that leads to common mode current on this, just using this guy. And then you analyze that. Now, we need to use this maybe on TART also to do connections, to qualify cabling and all that. So even in the Meerkat, we use this because they're all cables coming into the electronics. So you need to go to each single cable just to ensure that there are no coupling, there are no related emissions that have coupled into that's known as qualification. We've not done that with the Meerkat, but also just in the lab. A very nice project for maybe honors or EMC, just to characterize. You see, right now we are doing the Roche University is building a nanotech lab, and they're going to bring electronics there. We need a guy from physics to go and qualify what they have done just using this. You see, so there are numerous projects within RAT that we can do with the things that we already have, just on the EMC and RFI, and also on the electronics, right? but that also goes hand in hand with the programming, because sometimes these things you need to program them. Like what Tlaba did with the machine learning, use the data to find some RFI in your data. Yeah, I think that will be the end of our presentation. So just a simple demonstration of single antenna, receiver, and then what you see. So in the bigger scale is the TART array of antennas, receivers, all right? And then you collect that data, you transfer it, you have web interface, and then you see what's actually going on. The difference that this one, we are dealing with actual things on the ground, but for the TART, it picks things from space.